Hello and welcome to AP Calculus Lecture 5.1b. All right, where we're going to take derivatives of natural log functions, and some of our examples are going to be on page 319 if you want to open up there. So not much in the way of notes, mostly example problems today, but the one note you have is that if f of x is equal to the natural log of x, then f prime of x, the derivative of the natural log, is 1 over x. So think of x kind of as the blob. So it's 1 over the blob. All right, and then times the derivative of the blob. Okay, so let's do an example here. So let's say we have f of x is equal to the natural log of x cubed. All right, so I want you to think of this as a chain rule. So f prime of x is 1 over x cubed, but then times the derivative of x cubed. So times 3x squared. So that's going to be 3x squared over x cubed. And then that would reduce to, it cancels, right? Cancels 3 over x. Now that's the long way to do it. I want you always to think about rewriting using properties of logs, because it's usually much easier to do the calculus if you simplify the log. So we're going to rewrite this as f of x is equal to, what can I do with that 3? Bring it out front, 3 natural log of x. So then f prime of x is just 3, and the derivative of natural log is 1 over x. So that's going to be 3 over x. And as the functions get more complicated, you are really going to want to rewrite using properties of logs when you can. All right, our next example, let's say we have y is equal to x times the natural log of x squared plus 1. Okay, this is a product rule. So we have the first times the derivative of the second plus the second times the derivative of the first. So y prime is going to be the first, x, times the derivative of the second. Well, that's 1 over x squared plus 1. And then don't forget, you have to take the derivative of the inner function. So times the derivative of x squared plus 1, which would be 2x. Plus the second natural log of x squared plus 1 times the derivative of the first, which is just 1. So cleaning this up, we would have 2x times x, that's 2x squared over x squared plus 1 plus the natural log of x squared plus 1. All right, and you really can't simplify that any further. All right, let's do another example. Let's say we have y is equal to tangent x over 1 plus natural log of x. So this is a quotient rule. I can't really get out of using the quotient rule. Okay, so we would have y prime is equal to the bottom, 1 plus natural log of x, times the derivative of the top, secant squared x, minus the top, tangent x, times the derivative of the bottom. Derivative of 1 is 0. The derivative of natural log of x would be 1 over x all over 1 plus natural log of x all squared. So we can clean that up just a little bit. I can write that as 1 plus natural log of x times secant squared x minus tangent x over x over 1 plus natural log of x all squared. But you really don't even have to go that far. I would have been fine if you would have left it like this. The only thing I did was make this tangent x over x so that we don't think that 1 over x is part of the angle there. All right. Just a bunch more examples, but not a lot, not really any notes so much. So you're learning by example problem with this lecture. So example 42, this is on page 319. We have h of x is equal to the natural log of x squared plus 3, and we want to find the derivative of that. So h prime of x is going to be 1 over the blop here, 1 over, so this is a chain rule, x squared plus 3 times the derivative of this inner function, which is 2x. So that's going to be 2x over x squared plus 3. All right, next example will be number 48. So here we have f of x is equal to the natural log of x over x plus 1. Now this is one where you absolutely you want to rewrite this as you want to use properties of logs and rewrite it as f of x is equal to the natural log of x minus the natural log of x plus 1. That's the whole reason we did lecture 5.1a, to remind you of the properties of logs. If you do this as 1 over x times x over x plus 1 times the derivative of that, you've got a tremendously difficult problem. You can do it, but it's so much easier. Always rewrite if you can. I'm writing that down. Always rewrite. Okay, so f prime of x, this is an easy derivative to take. It's going to be 1 over x minus 1 over x plus 1, and then derivative of x is 1, derivative of x plus 1. So that's it. That's all you have to do. Now the back of the book is going to combine these fractions. So remember, what you do is you multiply the denominator, so have a common denominator, x times x plus 1. We're going to bring x plus 1 over to this side, and then bring this x over this side. And then you end up with just 1 over x times x plus 1. If you want to distribute the x, you can, but that is completely fine there. All right, let's do example 52. So that's y is equal to the natural log of the natural log of x. Okay, y prime then is going to be 1 over this blop here, 1 over the natural log of x, times the derivative of the natural log of x. So that's 1 over x. So that's 1 over, we want to bring the x out front so that we know that it's not part of what you're taking. This is not the natural log of x squared. So I want to bring that x out front when we simplify into 1. Okay, okay, we're cooking right along here. Next example is number 60. Doing a lot of the even ones. We have y is equal to the natural log of the absolute value of the secant x. Now you can't take the natural log of a negative, so that's why we put absolute value symbols. So y prime is equal to 1 over secant x, but then we have to take the derivative of secant x. Well, that's secant x tangent x. Then what happens to the secants? They'll cancel, and all you're left with is tangent x. So that's beautiful. I love it when it simplifies down like that. All right, let's do number 62. We've got y equals the natural log of the absolute value of secant x plus tangent x. So y prime is 1 over all that, 1 over secant x plus tangent x, times the derivative of secant x plus tangent x. Well, the derivative of secant x is secant x tangent x. And the derivative of tangent x is plus secant squared x. So derivative of tangent, secant squared. Let's write this as one fraction. So that's going to be secant x tangent x plus secant squared x over secant x plus tangent x. Now, I want you to recognize that this is simplifiable. How about we factor out a secant x on top? If you do that, what you have left is tangent x plus secant x. And on bottom, we have secant x plus tangent x. Well, tangent x plus secant x and secant x plus tangent x, those cancel. They're the exact same thing. If it were minus, if one of them were minus, it wouldn't be. But they're plus, so they do. So all that's left, we can simplify this bad boy right down to just secant x. That is so cool. All right, I want to do one more. This one is implicit differentiation. So that's from section 2.5 and 2.6. And we have a relation, the natural log of xy plus 5x equals 30. So we've got our x's and y's all mixed up. So what you have to do is take the derivative with respect to x. So what I want to do then is rewrite this as the natural log of x plus the natural log of y. Let's use the properties of logs to split that up. Then it's going to be a lot easier to take the derivative. All right. We're taking the derivative with respect to x. That's going to be 1 over x. For natural log of y, it's going to be 1 over y dy dx, because we're taking this with respect to x, plus 5 equals 0. All right, we want to put 1 over y dy dx, put all of that on the left and move everything else over to the right. So equals minus 1 over x minus 5. So I took that 1 over x and 5, moved it over to the right. Now let's multiply both sides by y to solve for dy dx. All right, so it's going to be y times negative 1 over x minus 5. So our final, what we'll do is distribute the y. So I have minus y over x, and you don't really have to do that. You could leave it like this. So minus 5y as your final answer. So got x's and y's mixed up. Then you want to use implicit differentiation and differentiate with respect to x. Okay, so I think there's one of those on the homework. So I want to give you a big hint. Always, so I'm going to write this again. Rewrite using properties of logs. Properties. Is that right? When you can. Okay, do that first. So your homework is on page 319. You're going to do 41 through 51 odd, 55, 59, 61, 64, and then finally 69, which that one is implicit differentiation. So the first step, if you can rewrite using properties of logs and make it into, say, multiple logs, it's going to be a lot easier than if you don't do that. All right, use the, if it's, for example, on, let me do another example here that I didn't do. Let's look at example 46. All right, so that we have y is equal to the natural log of the square root of x squared minus 4. You want to write this as the natural log of x squared minus 4 to the 1/2 power, and then y is 1/2 times the natural log of x squared minus 4. That's how you want to rewrite it. And now take the derivative of it. Okay? Much, much easier than fooling with trying to take the derivative of it without using properties of logs. So do that. Use the sum and difference properties, but split them all up when you can. Bring those coefficients out front when you can, and then your life will be so much easier. All right, that does it for this lecture, and I will talk to you on the homework solutions.